Hello. In this video we will learn and see how to design a dam. We have already seen other videos about different types of dam. In the pictures we see are different dams such as rock-fill dam, concrete dam and combination of rock-fill and concrete dam. How to design these dams. How to fix their dimensions. In this video we will try to learn complete design of dam. Necessary of a dam arise when we see unutilized water is flowing in river in enough quantity which can be used for many purposes. It is always becomes the first step to estimate the quantity of water to decide how much water we can actually utilize. We all know water available in a river will not be constant in all years. In some years it will be more and some years less. According to our needs, we need to estimate the water availability corresponding to that requirement. Water availability is nothing but the estimation of river discharge. We all know that discharge is area of that section multiplied by velocity. Broadly, river discharge can be estimated by two methods. One is using measuring velocity and multiplied by area. Other is by developing rating curve. If we see the second method, that is rating curve. Right side image shows natural photo of a flowing river. If we just draw, we can see adjacent picture, we can see river cross section with blue line and we can see red color vertical lines in that cross section. Red color lines are gauges. We can see the gauge photograph. A gauge is nothing but having readings or level mentioned on that. These are placed on the banks of the river so that we can directly measure the water level. Now we have to use the rating curve. Rating curve is nothing but a graph of plot between elevation and discharge. That is when water is flowing at particular level, what is the discharge. We can see the rating curve graph here. For any river length or river of consideration stretch, we can find out or develop this rating curve using simple calculations. This can be developed using HEC-ROS software also. Generally, gauge reading method is quite useful in getting data very easily. Further, during high floods time, it is not possible to collect or measure the river velocity. During high flood times, just observing the gauge reading and with the help of rating curve we can estimate the flow in the river. The other method is area velocity method. The concept here is measuring velocity and multiplying it with area of river section. If we take one velocity reading and multiply with area of river section will be rough and it may not give accurate discharge value. Since the river section varies and also velocity varies. Velocity is different at banks and velocity is different at middle portions. In this regard, as shown in the image, river is divided into segments. Velocity is measured in each segment using current meter. Once the velocity is obtained, multiply with area of individual segment and adding will give the discharge value. Further, nowadays, latest instruments such as automatic velocity or sensor-based are available which gives velocity as well as discharge. Overall, we measure discharge flowing in river at suitable intervals. This may be every day or as per project requirement. As explained in other videos about the difference between QMEC and MCM, we generate yield values based on these observed discharge values. A series of discharge and yield are developed for further analysis. We have seen the collection and how we measure the discharge data. This data will be compiled in specific sheets as shown here. This can be daily data or monthly data or 10 daily data. In other videos of this channel, we have seen the difference between QMEX and MCM. Here we can see, data can be entered in daily format. That is, daily discharge in QMEX is entered which can be used for further analysis as required. Further, the same data can be converted to 10 daily series. Because, sometimes, we have to do simulation for many years together. Using daily data and doing simulation will take time and it is required only in specific and accurate studies. For broad idea of the simulation we can convert these daily data into 10 daily series which can be used in further analysis. We have seen the data collection. We will see how to process further. First we'll compile the yield in MCM for different years as shown like here. There comes concept of dependability. We all know dams are designed to meet for different purposes. Suppose if a dam is designed for drinking water purpose, we generally consider the flow corresponding to 100% dependability. That is, we design that project for the flow values which are available for 100% time. That is, out of those many years, least value of flow is minimum flow which is available in all the years. Some values will be higher than that, but we are designing for drinking purpose, we should consider 100% dependability. In similar way, we design irrigation project for 70% and hydro project for about 90% flow values. We will see the example here. First we have to arrange the flow values in decreasing order. Then each value is denoted as per serial number. Percentage is obtained by dividing the serial number by total number of samples plus 1. If you see here, 320 is highest value. Its serial number is 1. Its percentage will be 1 divided by 15. 15 is samples plus 1. Total samples are 14. Like this we derive percentage. We can observe here is that minimum value has highest percentage. That is, minimum flow is available for most of the time, whereas highest flows are available for less time. If we have to design for drinking purpose, we have to consider 100% dependability, that is, flow value of 100 mcm in year corresponding to 100 mcm is 2004. So further analysis we have to consider based on the flow values of 2004 year discharge values. This is how we can work our for other dependability as well as different type of purpose of dam. Once we have water availability data, next is to select dam site location. By this time, we know the river reach in which the dam has to be planned. However, we do not know the exact location of dam access. For this we have to consider more than 2 number of dam access locations to check the feasibility. We do not require any special studies for this. Based on the field visit, we can observe the geology, site conditions and river characteristics and so on. At the field we collect the data regarding field conditions including geology. Using the computers and latest technology such as digital elevation model DEM and other satellite data, we can generate approximate contours of the site to compare among the different alternative locations of dam. When we compile the above information, dam axis needs to be selected based on these aspects. The valley should be very narrow, because the wide valleys requires more material, hence increase in cost. Further, dam locations are preferred where rocks are exposed or good geology compared to other alternatives. As far as possible, straight reach of river portion is selected for dam axis. Further, depending on project layout, we have to consider the location accordingly. Dam axis where huge diversion arrangement and tunnels, powerhouse near to dam and so on are coming, the location should be sufficient enough or better compared to other alternatives. This way we can finalize 1 decameter site among many alternative dam sites. Like explained before, selection of dam site requires proposed project layout considerations. Here, we will see different project layouts. We all know that project layout is different for hydropower dams and irrigation supply dams. Here we see is layout of dam toe powerhouse. This type of layout is possible in 2 ways as shown in the image. One is directly having the powerhouse at the downstream of dam blocks, that is, water intakes are going through dam body as shown in the bottom image. Other layout is using tunnels. These tunnels are taken around the dam body through abutment and having powerhouse at the dam toe. So careful consideration is to be given with respect to selection of dam axis. Other type of layout is hydropower having all the components. As shown here, water enters from intake, then through head race tunnel, surge shaft, valve house, penstocks, generates the power at turbines and through tail race goes back to river. If project is proposed such type of layout, then dam access site shall be good enough to accommodate intake and also possible diversion arrangement during construction. We can see here layout of irrigation project. Here, the canals are planned only on left bank. In some projects, canals are planned in both abutment sides and also through dam body. Accordingly, dam site needs to be selected. Other aspect is diversion of flood during construction period. Diversion is possible using both upstream and downstream coffer dams. Sometimes, river width can be bifurcated and the flood will be diverted through other half and construction in other half. Where it is not possible, using diversion tunnels is necessary. Selection of dam axis should also include this point. Once we have finalized a dam site, then we will go for detailed study at that place. We have to collect the topographical information. This can be done by conventional total station and other surveying instruments. Further, latest technology such as drone survey can also be used. Once the survey is over, we have to generate the contour maps using the survey data. We all know contour is line joining points of equal level or elevation. As per project requirement, we have to generate the contour as per interval such as 1 meter, 2 meter or 5 meter interval contour maps. Once the map is finalized, then we can use this map for various purposes. Using this contour data, we can generate river cross-sections at any point. River cross-sections are useful for generating rating curve. Further, topo data is useful for generation of area elevation capacity curve. After completion of topo survey and contour maps, we have to develop area elevation capacity curve. This means a single graph showing the area corresponding to different elevations. Accordingly, the volume of storage also can be worked out. If we see here at the right corner, the river cross-section is indicated. River bottom level is 100 and if we want to see the curve up to 200, we will see how to develop this. We have to prepare a table with different contours starting from 100. The next column is area. We know that at bottom elevation, the area coming under this contour is 0. So area is 0 and accordingly the volume is also 0. Then the next is 120 contour. That is 20 meters above the riverbed. This contour will cover some area and accordingly the volume between 100 and 120 is estimated using formulae like trapezoidal formula for volume calculation. Like this, volume between two contours is worked out and cumulative is indicated in another column. It is always better to add or prepare the curve up to maximum possible to check all the possible options. In the graph, blue color graph indicates for area and orange color indicates for capacity curve. Once we finalize the area elevation capacity curve, next step is to finalize the dam levels. We know there are different levels such as FRL, MDDL and DSL. When we design project for say 75 years, some sediment will be trapped in the reservoir. This we have to estimate. That volume we cannot use. This is generally known as dead storage level. That means, if we plan any pipe or tunnel below this level will not function properly due to deposition of sediment up to this level. Further, the level of tunnel or pipe shall be above this level. To avoid any issues related due to aeration in tunnels, we need to create minimum submergence for tunnel entrances. This cover, we will add above the DSL to get the MDDL. That is minimum drawdown level. When we use water for irrigation or hydropower, water cannot be drawn below this level. Now the remaining level that is FRL, that is full reservoir level, has to be obtained by doing power potential studies and reservoir simulation studies. The basic concept here is with initial reservoir level and inflows we subtract the outlet releases, losses and other requirements to get the final level. We have seen the development of area elevation capacity curve. Now we do further analysis to fix the FRL. Here we do simulation. Generally, hydropower projects are runoff the river type and storage type. Runoff river type projects are designed based on daily flow, that is, whatever water is flowing in the river will be utilized to generate the electricity within the same day. So the above simulation shown is for the whole year. This year-long simulation is not applicable for runoff the river projects. This year-long simulation is required for storage type reservoir. That is, storage created in the reservoir will be regulated in the whole year to meet the requirement. Further, if we plan excess irrigation or more hydropower generation, over the year water level will come down below the minimum drawdown level that is not desired. This way we have to do the simulation to check whether the adopted FRL and the volume between FRL and MDDL are meeting the requirements or not. This simulation helps us to finalize the FRL. We have finalized our dam levels. We have completed our topographical survey and fixation of dam levels. If we see in the images, there are two different dams. For any dam to plan, we must know what is the geology of the foundation. Earthen dams can be placed on disturbed rock and soil of good strength, whereas concrete dams shown on right side image shall have to be placed on good rock. So we must know the foundation where we are getting good rock, disturbed rock or weathered rock. This can be known by doing some boreholes at the dam site. As shown in the left bottom image, for any river cross-section, we will plan some more boreholes preferably at the center, and on the abutments. The machine for boreholes will look like this. While doing the boreholes we have to collect the core samples as shown in the right bottom image. These core samples indicate the variation of geology along the depth. While doing the boreholes, we also have to do the water permeability test to know how the water is seeping in the foundation. As you can see in the above images, earthen dam as we are placing on disturbed or soil foundation, there are chances of seepage. To stop the seepage, the blue color extended to bottom is known as grout curtain. This will stop the seepage from upstream to downstream. It acts just like the core in center of earthen dam. For concrete dams, to stop the seepage, we have to grout up to sufficient depth to stop the seepage beneath the foundation. We have seen about boreholes. There are other techniques which gives fast and accurate data with limited applications. These are called geophysical investigations. There are several methods such electrical resistivity test, seismic refraction test and others. The images shown here are electrical resistivity. By placing the electrodes at some spacing and passing the current and measuring the voltage, we will know the resistivity of the foundation. Based on the resistivity values, we can estimate the geology. Based on the boreholes and these geophysical, we can plot or develop geological cross-sections as shown in the left bottom image. Two extra lines indicate one will be the overburden depth and other will be weathered rock. Below the bottom line it is good rock. For concrete dam, we have to excavate up to this bottom line. We have completed about geology. Now we have to estimate the incoming flood for which we have to design our dam. If we do not provide enough passage in the form of spillway, water level exceeds dam top and failure happens. This is the most common cause of dam failures. As you can see in the right image, for any dam to construct, we have to make the site dry by diverting the river water. Coffer dams are used for this purpose. This is the reason we should estimate the design incoming flood for main dam as well as the flood for diversion coffer dam. However, main dam will stay for more than 50 years and it should be safe during floods, so the design flood value we should estimate according to its dam height. If it is a small dam, we should estimate design flood for 100-year return flood. If the dam is very high, then we can go for 1,000-year return flood or more. Coffer dams are temporary for construction purpose, so the diversion flood is estimated for 25 years flood or according to the dam complexity. There are many ways in estimating the flood. Important method is by estimation of hydrograph. For this first we have to delineate the basin up to the dam point. Based on the basin character, we have to estimate the unit hydrograph. Unit hydrograph means for 1 unit rainfall how the basin is responding and how much flood we are expecting at the dam site. Next step is to estimate the design rainfall. Generally every country has grid rainfall data according to the return period. For that particular return period, that rainfall is multiplied with unit hydrograph ordinate values, we get the design hydrograph. The peak of the graph gives the design incoming flood for which we have to design our dam. Other method is if we have measured river data, we know the peak values of each year. Peak values of each year are used to estimate the design flood according to the Gumbel method for different return periods. In similar way we have to estimate the diversion flood for coffer dams. We have finalized the design flood. Now we have to fix the spillway type and its dimensions. There are different types of spillways. If the flood is less and there is enough space and dam height is less, we can go for ungated spillway. As seen in the image, length will be more and discharge will be less. If we want to have control over the outflow and to increase the passing flood, we can have OG spillway. Here different type of gates we can have. If the design flood is more, and there is no enough space to provide the OG spillway, the best solution is orifice type of spillway. We all know that discharge is proportional to head. In this spillway, head is increased by lowering the spillway. This is used for passing high discharges, and also sediment also can be released through this spillway as these are placed much below. The other type of spillways as per the project needs are sluice spillways, siphon spillways and shaft spillways. For earthen dams, side channel or chute spillways are also used. Separate video of spillway types has already there in this channel. We also have to fix the dam type because we have gathered all the information we required. Here we can see the different type of dams. Based on the material type is shown here. There are other types of dams say based on the purpose and so on. Basic difference is material type. Concrete dams, earthen dams, rubber dams, steel dams and masonry dams are there. Under each category we have further different dams. In concrete dams, we have conventional concrete dam, roller compacted concrete dam, arch dam and coalcrete dams are there. Roller compacted dam is placing concrete in layers and rolling just like in earthen dam. In earthen dam we have four main types. One is homogeneous dam. These dams are generally low-height dams. To have high dams and to have seepage barrier, we introduce core in the center of dam, that is central core earthen dams. Further to optimize, inclined core dam type is also used. Further optimization, we have concrete face rock fill dams and geomembrane face rock fill dams. That is impermeable membrane, either concrete or geomembrane is placed at the upstream. We have seen different types of dams. We have fixed spillway type. This is an important step. If the geology is poor, we have to go for earthen dam. Further, if the dam length is more also we can think of earthen dam as it becomes cheaper compared to concrete. Further, if the spillway length is more and also if we have dam toe powerhouse as shown in the right bottom image, we have to go for concrete dams. Left side image we can see it is rock-fill dam with side channel spillway. Design flood might be less and also foundation also might be weak. Right top image shows combination of concrete and earthen dam. Concrete dam portion is used for spillway and dam toe powerhouse. Right bottom is completely concrete dam. This is how we have to fix the dam type, keeping the view of spillway size, cost, foundation and so on. We have finalized our spillway type and dam type. Now we have to fix our dam top. Before that we have to see whether our spillway capacity is sufficient to pass the incoming flood or not. If our spillway capacity is sufficient, then there will not be any rise in water level. However, sometimes due to many reasons, we might not provide sufficient spillway size. In that case, due to high incoming flood, there will be rise in water level. This level is called as maximum water level. This can be worked out by simple flood routing studies. That is, inflow minus outflow will be change in storage formula. Change in storage will cause increase in storage. As we can see the graphs, inflow peak is high whereas we can pass less than the inflow. That is shown in outflow curve. This peak is less than the inflow curve. This change will cause rise in water level by adding to storage. This is called maximum water level. Over and above this we need to provide freeboard to fix the dam top. This can be done by freeboard calculations. We need to estimate the wind speed, fetch of reservoir, and with the prescribed method, we can estimate the freeboard. Winds blowing over reservoir will increase significant wave height and it forms the basis for freeboard calculations. Freeboard is very important for all the dams. Once this dam top is fixed, we can now go for stability analysis to finalize the dimensions of dams. We all know that dams should be stable at all the times. This can be checked by stability analysis. Concrete dam stability is different and earthen dam stability is different. Concrete dams are generally called as gravity dams, because weight of dam is adding to the stability. whereas as earthen dams are soil type and strength comes from shear resistance of soil. This is the major difference. If we see concrete dams, we have to the stability check for sliding, overturning and stresses. Sliding means if the horizontal force is large and there is less resistance force, dam will slide in horizontal direction. The interface between the concrete and rock gives the necessary friction to resist the horizontal force. Further overturning is also required to check due to various loads try to destabilize the dam. If we see further detail, how to do the stability analysis in the right bottom image. We have to estimate the different loads. Self-weight of dam, weight of water if any on the dam body due to dam shape. Then we have to work out water pressure that is hydrostatic force. We also have to calculate uplift force. Water tries to seep from the foundation. There will be some pressure develop along the base of the dam. This will act vertically upward reducing the weight of dam. We also have to estimate the earthquake condition forces. For this first, it is necessary to estimate the earthquake coefficient of that area to suitably incorporate into the dam calculations. Once all these forces are calculated and we can estimate the sliding check and also stresses. For stresses we have to calculate the moments about particular point say toe or heel. Further, nowadays, many softwares are available. It is recommended to use the softwares as shown in the right top image to check the complete dam behavior in FEM analysis. Generally dam stability we have to do for different load combinations. It is rarely possible to have flood situation and earthquake together. So we have to identify the load combinations and accordingly we have to do the stability calculations. As explained already, earthen dam stability is different. Here we have to check the slope stability. Upstream slope and downstream slope we have to do the separate analysis. The curves indicate slip circles. There are many methods. Each slip circle is divided into many slices to estimate the resisting force and driving force. Accordingly we can estimate the factor of safety. This can be done in hand calculations. But nowadays, slide software is there and other softwares are also there to reduce the time and effectively compute the factor of safety. Here also for different cases we have to do the stability such as steady state seepage condition, sudden drawdown and so on. Once we complete the stability, it is always necessary to do the seepage analysis to estimate the depth up to which we have to do the grouting for concrete dams. For earthen dams it gives the important information whether to adopt any particular seepage measure in the form of curtain grout, diaphragm wall and so on. Further seepage analysis gives the total quantity of seepage and also exit gradients. We have to now focus on how we dissipate the energy of water passing through spillway. These water will be coming with high velocity and energy. If there is no proper energy dissipation arrangement, it will create erosion at the downstream of dam and may create stability and failure issues. There are two types, stilling basin type and bucket type. Stilling basin is based on hydraulic jump calculations. Based on the available tail water at the downstream energy is dissipated. For this we have to do the hydraulic jump calculations and also we have to fix the dimensions of stilling basin. Other type is bucket type as shown in the right images. Here water will be allowed to flow like a ski jet. Water will be thrown away from dam using ski jet action. We need to estimate the ski jump calculations such as throw distance and also water where it falls we have to see it should be erosion free. If the hard rock is there, it will not create much problem. If the erosion is more, we have to create a plunge pool that is preformed pool with water to avoid any erosion. This is how we have to finalize energy dissipation arrangement and complete the major dam design. Major dam design was explained. The other components design is also necessary. Other important components are gates and slope stability. There are different types of gates. We can have vertical gates, radial gates. Depending on the type of function, vertical gates can be wheel or sliding type. Further, to lift and place these gates we should have hoisting arrangement. In general we have rope drum hoist, hydraulic hoists and so on. We will have to design large girders or gantry cranes also in this aspect. Further, while constructing the dam, we also have to check the dam slope excavation stability. We also have to design dam piers and accordingly work out the requirement of grade of concrete, dimensions and reinforcement and so on. This is how we complete the total dam design, from initial water measurement, site selection, investigations, type of dam selection, dam stability and other components. Thank you.